Hi, I'm Chuck, and welcome to this video where we are going to take a look at second order linear differential equations that have constant coefficients and are homogeneous. That's a whole lot of description there. Basically, what that means is we're working with an equation like what you see here at the top. Second order means there's a second derivative involved. Linear means that none of the dependent variables, the y values in this case, are to any power other than the first power. Constant coefficients is going to mean that the A, B, and C are just real numbers. So there's a whole lot of information given in the name itself. Okay, so we're going to be working with equations that look like this. An example of something like this, I'll just make up something, might be 2y double prime minus 3y prime plus 7y equals 0. Homogeneous equals 0. So that's an example of something like we're going to be looking at. First thing I want to remind you of is that we're going to have two solutions for this. We can apply the law of superposition, or the principle of superposition, that says that we can create additional solutions and they'll all be in the form of some constant times the first solution plus or minus some constant times the second solution. Essentially what this means is that you're going to wind up with um, solutions that are linearly dependent on the first two solutions that we obtain. So when we obtain two solutions, basically from that we can create an infinite number of additional solutions, all of those linearly dependent on the two solutions that we've already solved for. When we solve an equation like this one up here, okay, we're going to be looking for solutions in the form of y equals e to the rx. And what we're going to need to do is to determine the value for r in the exponent. Okay. When we take the derivative of this, we are going to wind up with two additional values. We're going to have our first derivative is r e to the rx, and our second derivative is r squared e to the rx. When we take these values, y, y prime, and y double prime, and substitute them into the equation that we have up here, okay, what's going to wind up happening is this e to the rx is going to be substituted in for y. The y prime is r e to the rx, and that's going to wind up there. And, let's see if I can get this, there we go. The y double prime, which is r squared e to the rx, is going to go there in the equation. And when we substitute these in, this is going to give us the equation that we see at the top of the screen now. Notice in this equation that we have an e to the rx in each of the three terms, so we can factor that out, which leaves us with e to the rx times the ar squared plus br plus c equals 0. Remember, this is a homogeneous equation. Real important to remember, e to the rx is never 0. Aha! So what that means is this can never be 0. That therefore tells us that this quadratic equation we have here, this is referred to as being the characteristic equation, has to be equal to 0. Okay, since e to the rx is not 0, and we have two things multiplied together to give us 0, if the first thing isn't 0, the second thing has to be 0. You may recall back to solving quadratic equations, and with quadratic equations, there are three possible outcomes as far as the solution. You can have two unique real roots. You can wind up with a double root. Or the last thing that can happen is if in the discriminant, remember when you're solving this, you're going to need to use the quadratic formula, which is a negative b plus or minus the square root of b squared minus 4ac all over 2a. This component inside of the square root is called the discriminant. It allows you to discriminate between real and complex solutions. If that winds up being negative, what we're going to wind up with then is the third option, two complex roots. We're going to take a little time here and consider what happens when you get two unique real roots. We wind up with solutions R1 and R2. With these two solutions, okay, if we recall up here at the top of the screen, remember our y, our solution is going to be e to the r times x, but r is the root. Since we're going to have two roots because a quadratic has two solutions, okay, it might be a repeated solution or it might be two unique solutions. Either way, we're going to wind up with two solutions, y times c1 e to the r1x, and then we're also going to have y2, where in this second solution, we wind up with the second root in the exponent. Okay, so based on the principle of superposition, we can write a general solution in the form where we have some coefficient times the first solution plus some coefficient times the second solution. And any solution that we have or find thereafter is going to be some result of this scenario here. Now, we can prove that this general solution, the general solution I'm referring to being this, actually works by looking at our original equation, our ay double prime plus by prime plus cy equals 0, and computing the first and the second derivative of our general solution, which has the big yellow arrow pointing at it. Using that general solution, and I've written it down here for you, we can compute the derivative, okay? And that's just going to give us c1 times r1 e to the r1x plus c2 r2 e to the r2x. We can also, from our original general solution, compute the second derivative. And that's going to be as listed here, c1 r1 squared e to the r1 x plus c2 r2 squared e to the r2 of x. Then what we're going to do is we're going to take these three equations that we have here, and we're going to substitute those back into our original equation. Recall our original equation was a double prime plus by prime plus cy equals 0. So what's going to happen is this is going to go in, not going to go in there. This is going to go in for y. This is going to go in for y prime, and this is going to go in for y double prime. When we make each of those substitutions into that equation, we wind up with the equation that we have right here. I got a little yellow star to the right of it. Notice in this equation, you have terms that have a factor of e to the r1x and terms with a factor e to the r2x. You also have terms that are multiplied by c1 and terms that are multiplied by c2. If I go through here, distributing out the a, the b, and the c, and then regroup and factor out the c1 e to the r1x, I have this equation here. Factor out the c2 e to the r2x, we have this equation here. Now, the cool thing to remember is, first we know that the c e to the r1 of x is not 0. This can't be 0. The same thing is true, this can't be 0. However, having used the quadratic formula, we have our two roots, r1 and r2, and we know that these roots cause this first quadratic equation to equal 0. And the second root causes this second equation to equal 0. So what we have is something or other times 0 plus something or other times 0. Well, you're just going to have 0 plus 0 is 0. And sure enough, it works. Okay. the left-hand side of this actually does wind up equaling 0, which proves that our general solution right there is a solution. Now, notice we have a value C1 and a value C2. These are constants. They could be numbers like 2, 3, -7, square root of 5 over 4, 2/3, you name it, it's a possibility. The way that we solve for these is we need to be given some initial values. Notice in our general solution, we have two coefficients we need to solve for. We need to solve for C1 and we need to solve for C2. What this means is in our initial values, we need two pieces of information. You need two pieces of information to solve for two constants. Okay, so what's going to wind up happening when you're presented problems, it will typically be the case that you're going to be given some information if it's an initial value problem. For example, maybe y of 0 equals 4 and y prime of 0 equals 12. Realize that in the real world, okay, these two pieces of information, these initial values, and the reason they're referred to oftentimes as initial values is they're at time 0. It's a starting value. Now, even if it doesn't start at time 0, it's still referred to as an initial value problem. But oftentimes it'll give you the information at the start because that's what you know is going on. Okay, so what's going to happen is to solve for C1 and C2, we're going to need these two values here in yellow. Realize that if, for example, we were looking at an equation that described something that you threw in the air, maybe you threw a ball up in the air, recall that the equation for the location of that ball over time is going to be a -16 t squared plus v sub 0 t plus s sub 0. Here, the original equation describes the height, and y sub 0, this would be the height at the start. When we take the derivative of this, okay, this is going to be a measure of the change in position. This describes the velocity. This second piece of information here would be used in the velocity equation. And what this second piece of information tells us is initially the velocity is 12. I don't know what the units are on it because I'm just kind of making this up on the fly. We're not really all that concerned about units and things at this point. Just realize that the initial values actually mean something in the physical realm. Okay, it's not just two numbers that magically appear out of nowhere and have no basis in the real world. Okay, let's take a look at an example of this. How does this work? Here we have a situation where we have a second order. How do I know it's second order? Second derivative. Linear. None of the y's, whether it be y prime, or y double prime, is to any power other than the first power. It's second order, it's linear, it's homogeneous, it's equal to 0, with constant coefficients. The coefficients are 1, 6, and 8. When you have something like this, these are really straightforward to solve. Recall that you can take this equation and develop the characteristic equation. Wait a minute, where'd that come in? The characteristic equation is up here with the red ink. There it is. It's the AR squared plus BR plus C equals 0. And we talked about already where that comes about. Okay, we don't need to revisit that. We can look at this, say, you know what, it's second order, linear, constant coefficients, homogeneous. I'm good. I can go straight to a characteristic equation. The r squared is going to have the coefficient off of the double prime. The r is going to have the coefficient off of the first derivative. And the constant is going to be the coefficient off of y itself. It's going to be equal to 0. This is really nice because all we have to do now is to solve a quadratic equation. In this case, it factors readily into r plus 2 times r plus 4. It gives us our two roots. The first root is r equals -1. The second root is r equals -4. These are then substituted into our general solution, and that's it. You have a general solution for this particular differential equation. Seems too good to be true, doesn't it? Actually, that's about all there is to it. Now, I mentioned that we can go ahead and we can solve for the values C1 and C2 if we're given some specific initial information. Well, I'm going to use this same differential equation and we're going to provide some initial values for it. Okay, so what's going to happen is we know our general solution right here. I'm just going to bring this down. There it is. And let's take a look at our initial values. Our initial values are the function is equal to 1 when the x value is 0, and the derivative of the function is equal to 3 when x equals 0. Okay, well, I can take and compute the function itself. I want that because I have some information about y. So I'm going to want to look at y equals our general solution. It's right there. When I have this, I know that the y value is 1. We're given that, 1, when the x value is 0. Okay, so if I substitute 0 in here and 0 in there, each of those factors is e raised to something or other times 0, so it's e to the 0, which is just 1. And what that gives us is the situation where we have 1 plus C1 plus C2. Next thing is going to be working with the derivative. How do I know I'm working with my derivative? Because one of my pieces of initial value information talks about the derivative of y. Taking the derivative of my general solution here, the derivative works out to be that. Need to use the chain rule a couple of times, but I'm sure that by this point that's no big deal for you. Then when we go to use the initial value with y prime of 0 equals 3, we're going to apply this to the derivative of the general solution. We're going to substitute 3 in for the y prime value. We're going to substitute 0 in for each of the x values, which is going to give us e to the 0 and e to the 0 ultimately, which is going to leave us then with a minus 2c1 minus 4c2. All right, so the good news is we have two equations, two unknowns. Now you get to use what you practiced back in high school with your algebra, solving a system of two equations and two unknowns. Probably the easiest way to do this one would be to multiply the first one by 2 and add them together. So I'm going to get 5 is equal to 2c1 minus, 2c1 minus 2c1 cancels out. 2c2 minus 4, so this is going to give us a minus 2c2. So this allows us to then determine that c2 is equal to a negative 5 halves. From that, we can go ahead and solve for c1. Let me check here, make sure everything's working good. We have a 5, those are canceled, minus 2. Okay. Taking the negative 5 halves and substituting that in for C2 means we're going to add 5 halves, okay, and that's going to give us C1 is equal to 7 over 2. With that information, that allows us to then provide for a particular solution, and that particular solution is going to be y is equal to, now be careful, I'm looking at the top of the screen, C1, so that's going to be 7 over 2 e to the negative 2x plus C2, well, that's going to be a negative 5 over 2 e to the negative 4x. There is our particular solution based on the initial values that are shown at the top of the screen. We can also derive a formula for general solutions for a double root and a complex root with approaches similar to what we used up here, okay, when we got into all this moving things around and good stuff like that, okay? Um, what I'm going to do is skip that for right now and just say, look, when you wind up with second order linear constant coefficient homogeneous equations, you can go straight to a characteristic equation. And from that, you're going to have one of three scenarios: two roots, a double root, or complex roots. If you have the two roots, your general solution is going to be in this form. That's what we just saw. If you wind up with a double root, it's going to be like this. Now notice, there are a couple things on this double root that can escape your notice at the first look. There is just a single value for r, which makes sense because you have the same root twice. The difference here is the second term also has a factor of x in it. That's not a mistake. It's supposed to be there. All right, if we get into complex roots, what's going to wind up happening is our r values are going to be in the form of a complex number. So we're going to have alpha plus beta I and alpha minus beta I. The solution form that we're going to wind up with is this one. Now, the good news is, regardless whether you have two roots, a double root, or a complex root, the bulk of the heavy lifting is already done because you have a general solution. The only other thing you might have to deal with is finding a particular solution based on some initial values. Okay, so we have these three forms of general solutions based on the results of the quadratic formula. Let's take a look at a couple of scenarios. In this case, we have y double prime minus 8y prime plus 16y equals 0. This can be rewritten as r squared minus 8r plus 16 equals 0. Remember, we're actually going to factor out an e to the rx, okay, as we saw earlier. But what we're really after is the characteristic equation. Because it's the characteristic equation that's going to be equal to 0. It's the characteristic equation that'll give us our roots. This factors into, oh, let's see here. This is going to be an r minus 4 times an r minus 4. This gives us a double root of r equals 4. As soon as you see you have a double root, you're close to done. All you need to do is use the formula that's provided at the top of the screen. Well, that formula is going to be y equals c1 e, remember we only have one root, that's 4x, plus c2 x e to the 4x. The only thing that can make this entertaining is if you're given some initial values, then you would need to solve for c1 and c2. Let's take a look at a third scenario. Here we have, once again, a second order linear differential equation, constant coefficients. Wow, they're all 1. Okay. Let's go after this. As with the previous two examples you've seen, we can jump right to the characteristic equation. This is going to be r squared, coefficients 1. R with a coefficient of 1 plus a coefficient of 1 equals 0. Now, you may know from your previous experiences trying to factor things that this is going to be a problem. To solve this, I'm going to set up my r equals, normally it's x, but here our roots are r. It's going to be a negative b, so it's going to be a negative 1 plus or minus the square root of b squared. Remember, b is the coefficient there. That's 1 squared minus 4 times a times c, so that's going to be minus 4 all over 2 times the a value, which is that 1. Okay. Simplifying this, we wind up with our root is equal to a negative 1 plus or minus. Notice it's going to be a -3. So this is going to be I times the square root of 3 over 2, which means that our roots are going to wind up being a -1 over 2 plus or minus the square root of 3 times I over 2. So there are our two roots. Recall that this first term is alpha. The second term is beta. Okay, so with that done, you can now go after your solutions. Oh, look, right there they are. Okay, we're going to have y equals e to the alpha x. I'll just copy that down again. We have y equals e to the alpha x times, now if you take a look here, you're going to have c1 cosine beta times x plus c2 is going to be sine of beta times x. Okay, with that, you're ready to go. You can write down your solution at this point. Y is equal to e to the alpha. So that's going to be e to the -1/2 x times c1. We don't know what that's going to be because we do not have an initial condition. Times the cosine of beta. Well, that's going to be the square root of 3 over 2 x plus c2 times the sine of beta is going to be our square root of 3 over 2 x. And we'll slide that bracket in. Now, you may be thinking, well, wait a minute here. This could be a positive or negative square root of 3 over 2 in this cosine. But if you remember back to your rules with trig functions, cosine of positive x is equal to cosine negative x. So it doesn't matter in that term whether we wind up with plus or minus. For the second term, we could have plus or minus there. But remember, the sign of negative x is negative the sine of x. Oh, so that negative sign just kind of gets absorbed into the C2. So you're good to go. I hope this makes some sense, and I wish you the best with these.